How's everyone doing today? I'm sleepy. Hungry. That's my answer every single day, isn't it? Clearly something needs to change. This is a me problem.
I was about to say, at least you're not hungry for anything.
Yeah, I was. What time do you go to sleep?
Anywhere between 10 and midnight, depending on what I'm doing and how long my phone call with my fiance goes.
And then wake up?
8-ish.
That's a lot of hours.
I know, and yet.
It's like 10, 9.
8, 7, 6, 5, 4, 3, 2, 1. Because of the time between first meal and second meal is too great, I need a snack.
I feel that way about lunch and dinner. It's like a really big gap.
Yes, I was recently shown an article about how it is usually a very good idea, scientifically speaking, to have a mid-afternoon snack. Because if you go like about 6 or 8 hours between lunch and dinner without eating really much of anything, you're just going to feel really hungry at dinner and eat a lot. Which, if you are very hungry, you need the food, but sometimes you feel more hungry than you are, and you overcompensate. So I've been working on mid-afternoon snack. I think that's a good idea. Maybe a mid-morning snack too.
It's like better to eat like bunch of mini small meals.
Yes, we all need to move towards the Hoffman model of having first breakfast, second breakfast.
First lunch, second lunch.
Yes.
Not too much. I get 4, not like 6 meals.
Oh, not all meals.
So like-
Maybe just snacks.
Some
I
cheese.
like my lunch to be nice and big though. So you can sit down and I can enjoy it while I'm resting in the middle of work.
Lunch is my least favorite.
Really?
What? I like dinner.
Breakfast is long.
I don't like breakfast food, but I like breakfast.
I like, most of my favorite foods are lunch/dinner foods. So breakfast is usually underwhelming for me. Because very rarely does breakfast get to be a burger. Okay. Any, and any at all, questions, comments, needs, etc. before we begin today? Vector's on. Dr. Odekar was using it literally an hour ago. I was not ready to fight technology today.
Only have the bowl. What is standby?
Hello, everyone. Welcome to Technology Hates Me. How are you today? Spend your whole life studying science and then it betrays you.
Did you press yes or no?
Yes.
Press no next time.
Well, no, I was meaning to turn it off, to try to get it out of whatever not working mode it's in. Now it's not. Turn it back on.
It's blinking,
Blinking? Is it blinking about something?
blinking green. Does that mean turning on or off?
I don't know. At this point, I'm too sad and confused now.
The other wire, do you think it's supposed to be on this? Oh, it's red now, so it's off now.
Takes it that long to shut down? Okay, so it is now rebooting. Hello, everyone. I'm just going to try to keep talking to distract myself from the existential sad I feel from not understanding my own machinery. So, physics.
It works.
It works. There we go.
Did you get the lab to work? Like where the eyes wouldn't melt?
Yes, the metal cups were not insulated enough. So when you instead mix the hot water and the ice in a styrofoam cup, things work a little more as expected, which is entirely on me for how I redesigned the lab. That will be corrected for future iterations. So if you had lab on Tuesday and the ice didn't work as expected, it's because of the changes I made. And again, I'm not going to hold that against anyone in the grading. We get checking grading based entirely on your algebra. If you have lab today, I have everything figured out by now. And all of these things not working right is a perfect example of entropy, isn't it? To try to somewhat railroad things into where we need them to go. We have at least talked about the definition of each of these very briefly last time. And we're going to go through each of them more in depth today and tomorrow. Before that, just a couple of keywords that show up in most of them. The system is usually whatever you are specifically studying in a given example. So we are going to spend a lot of time today and tomorrow looking at pistons, and by which I mean usually a metal cylinder with a smaller metal cylinder coming out the end of it that is designed to expand or contract to push in or out on whatever it's attached to. And these usually work by having a plate inside of the cylinder attached to the actual piston, part of the piston. And then inside of the cylinder is usually some type of fluid. I'm mostly going to be drawing a gas for this particular example. If we are examining what is happening to this particular object, this is our system. And the universe, the surroundings, is everything that isn't this thing. Whatever isn't the system you're looking at is the surroundings.
Wait, is the piston surrounding?
No. We are examining what happens to this particular series of objects, that this is our system.
But if you're just talking about like that one chemical reaction, then the piston is surrounding.
Yeah, if we were just looking at the gas, then the piston itself will be surrounding, yes. Which is why in every single question, it will be defined what parts of the system you're looking at. Usually, we'll be looking at the whole piston, what the whole thing is doing, and that would be the system, and everything that isn't the piston would be surroundings. Sometimes you are insulated from your surroundings, sometimes you are not. Questions will always say whether or not you are insulated from your surroundings, and that each question is going to be a little bit of a case-by-case basis, but each problem will specify whether or not energy can flow into or out of your system from the surroundings. For simplicity's sake, we're frequently going to assume we are insulated, but sometimes the point of a problem will be that energy is flowing in, and then what happens? So. Now, each law in brief. The most basic one is the newest one, the zeroth law. And it's just the communicative property of temperatures, as we've stated. If A and B are at the same temperature and B and C are at the same temperature, then A and C must be at the same temperature. This law was literally written as a prologue to the other laws, which were written before it. So, looking at the first of the actual laws, we have the first law of thermodynamics, which you've been interacting with most of your science classes for forever. And the heat on, right?
To use that new air conditioning system.
Well, this part of it isn't new, that's for sure. This is just, the technology doesn't work today, isn't it? Or is it just things around you don't work? Okay, so the original definition of the first law of thermodynamics, as written on the previous slide, is energy cannot be created or destroyed. It can only change forms, and it can only swap what object has it. That is the universal first law of thermodynamics. We can scale it back to look at specific systems in question. If we're looking at a specific system, we can rewrite it to say that the increase in the internal energy of a system is equal to the amount of work, the amount of heat added to the system, plus the amount of work done on the system. That is from the perspective of the surroundings. Whatever you are looking at, this first statement is from the perspective of whatever is surrounding the system you are looking at. If we are looking at things from the perspective of the system itself, and we're going to do most of our questions from this perspective, the increase to the internal energy of a system is equal to the amount of heat added to the system minus the work done by the system. Go ahead and write that formula down. We'll study it and use it today.
So, if you have a positive delta U, does that mean, and a positive delta H, which is enthalpy, you know what that is, right? Yeah.
Yes, although I admit I don't use it a whole lot in this class.
Does your work have to be positive too? I don't know when to determine if work is positive or negative.
It entirely depends on the perspective of the object you're looking at.
The system.
So from the system's perspective, if the system does work, so if the system in question is a human being, and the human accomplishes work, energy is leaving them. If I do work, energy has left my body. When I lift marker, now the marker has GPD, which used to be chemical energy in my body, now it's GPD in the object.
So if I had a piston and it was like this, and then after the reaction it was like this, The work done.
Work was done, it was done by the piston, because whenever a piston expands, it exerts a force as the actual piston part moves a distance. So if the piston is ever expanding, it is doing work on its surroundings.
So, positive? I don't understand the positive or negative. How can you have a negative work? I get positive work and no work.
Okay. This is what we're talking about today.
Oh.
So I'm glad you're asking. So, I will be using this version of the formula, the formula from the perspective of the system for most of our work, which is why it's on the board, which is why I've written it. Sorry, which is why it's in the notes and it's why it's written right here. So, from the system's perspective, from the perspective of whatever you are looking at, we'll start from a piston. We're going to do those examples a lot. I've already brought it up. From the perspective of a piston, I'll redraw it over here. From the perspective of some type of piston, it has, but nothing's changing, we're just examining it as it sits cold on a table. This object has some amount of energy inside of it. If nothing else changes, nothing else happens around it, that total internal energy level stays the same. Which means that delta U, which is the change in internal energy, would be 0 as long as nothing is happening to it. Now, if for any reason at all, the piston expands, it is then doing work on its surroundings. Because the old formula for work, which is going to be revived for these formulas, work equals force times distance. When this particular piston expands, it's going to exert a force as the end of it moves some distance. So it is doing work on its surroundings. And work is really just energy. So positive or negative work is just meant to tell you what direction the energy is going in. So I like this color green, so I keep looking for this one. So from the system's perspective,
It being the system?
correct. From the system's perspective, positive work means the system. You can replace the system with whatever you're studying. So positive work means the piston is doing work and energy is going to leave the piston. That's why there's a negative sign in this version of the formula. If the piston is doing work, energy is leaving it, and that means that if no thermal energy changes throughout this whole process, if we're just looking at total internal energy and work done by the device, if the object does work, that's going to drive down its own internal energy level, because it now no longer has the energy that it put somewhere else. Anything that does work, it's sending energy out of it somewhere else, someplace else. It's true with your arm, it's true with this machine.
How do I know that the energy left?
Sorry.
How do I know that the energy left? Like for positive work, energy leaves?
Energy's weird in that you can't see it, you can only see what things do when they have it. example I like to use for this is old-timey train wheels. Old train tracks, well, actually, trains that still run through Clinton still have this.
Did I really?
Well, most trains on American rail systems still have this. Japanese super magnet trains don't. But most trains, past and present, have a piston, and part of that piston is going to expand. As it does that, it's going to drive the part of the wheel it's attached to forwards. And you can tell that the wheel now has energy because the wheel is moving.
So it left from the piston to the wheel.
Yes.
So expanding is leaving,
Yes.
compressing is, I don't know. What is that?
When something outside of the piston was to come in and compress it, that would be doing work, the surroundings doing work into the piston. Which means that the system would be gaining energy. Now, from the system's perspective, if we plug in a positive W for the system doing work, we would plug in a negative W for work being done on the system. That negative would get negated here, which would drive up the internal energy of the system. When you do work on the device, it now has more energy than it had a second ago. And exactly what that looks like depends on the other factors of your particular system. If you drive up the internal energy level, your temperature will rise. Sometimes, if this stays constant, the machine will just dump out thermal energy instead.
So like the top one is W equals Q plus W, basically?
Right. This version of the formula is based on the statement right here, from the system's perspective. This is from the surroundings perspective, but it's the surroundings perspective of the device.
The first one?
Yes. So if we were looking at this particular piston on the side of the train, this formula is from the piston's perspective of what it is doing and what is happening to it. The top statement would be the train's perspective of the piston. Excuse me.
So the train has negative work because, or the wheel, because work is being done on it.
Work is being done on the wheel,
Yeah.
yes,
So,
which means the wheel is gaining energy into itself.
so it is negative work.
That's a
From the
negative.
wheel's perspective,
Yeah.
yes.
Yeah.
Using this formula, from the wheel's perspective, when work is done on the wheel, correct. It will
Okay.
gain energy, work's being done into it, plug in a negative work, which would be a positive energy gain for the wheel.
Yeah.
Yes.
Once you get to work, can you finish the negative work?
Yes, absolutely.
You just knew.
Is that obvious when I get thirsty? Negative work means the system has work.
Why did you put that?
I don't know, to match how I had it before.
Okay.
You can put any word in there. Positive work means the piston is doing work and energy leaves the wheel, the train. I don't know. It looked like that and I wanted it to be symmetrical. My brain is weird. Negative work means the system has work done on it, and it gains energy. And the formula is set up like it is because from the object's perspective, when it does work, energy is leaving it. When work is done on it, it gains energy. Which is the only reason we have this negative here in the formula. So you could reverse it. We could put a plus sign here in terms of positive work versus negative work. But because we're looking at it from we're trying to examine what the energy is doing, because this is the thermodynamics chapters. This version is mostly about energy direction. Positive work means energy leaves the object, negative work means energy enters the object.
Okay, can I ask something?
You absolutely can.
So, your hand lifts a marker. Your hand did work on the marker.
Mhm.
Energy left your hand and went into the marker.
Yes.
So, you did positive work, but the marker received negative work.
Yes, it's a matter of the perspective of each part of the system, each object.
Okay.
From my hand's perspective, my hand did positive work because energy left it. From the marker's perspective, work was done on it and it gained energy.
So like, is it gaining like, in that example, potential energy?
Correct.
And then what did you lose? What kind of energy did you lose? Like kinetic or something?
This is erring on the biology side of things. I believe the chain of events would be chemical potential turned into kinetic while my arm is moving, and then it transfers into the marker.
Okay, yeah.
Any other questions? Okay. I want to skip to the next couple of slides because there's some sample questions we can look at, put some numbers to all the hand looking at. The next slide is just further iteration about all the variables present. Q represents thermal energy flow into or out of the object in question. If Q is positive, that means the system has gained thermal energy from something. If Q is negative, that means it is losing thermal energy to its surroundings. W is work. In the version of the formula we're using, it is positive if the system is doing work. And then lastly, we have U, I should specify. Delta U is positive if the object's temperature rises. So, for example, if we're going to add thermal energy to something, but it doesn't do any work because of it, if we just put thermal energy into some rock, and it doesn't do any work because what work can a rock do? Its internal energy level will go up because we put energy into it that it then couldn't use for anything, and then its temperature will rise. It now just has that energy stored in it. So there are going to be cases where you put energy into something and then it uses it to do work and its temperature stays roughly the same. There's also cases where you put energy into something and it does nothing and it just holds on to that energy and gets hotter.
Could you could have lost your energy to like the surroundings versus the rock.
Yes.
That's why the rock isn't like steaming hot after you do it. Right? It's not like exactly that much warmer.
Well, it depends on how much thermal energy you put into it. But yes, the rock is touching things, so the rock can lose the heat next to its surroundings. Unless it... Now we're getting into more complex systems where we assume everything's touching. Okay. Small, sort of rapid fire examples, different types of cases that we can examine. They're all about a piston, so I'm going to put all the work over here. A piston remains at the same temperature as 1,000 joules of energy are added to it. How much work will the piston do?
It's negative 1,000. I'm confused.
Okay, it's okay. So we have our formula. We're going to add, we're going to do all of this from the piston's perspective. We're going to add thermal energy to the piston. So Q is 1,000. Piston's temperature will stay the same throughout this whole thing. What does that tell us about either of our two remaining variables? Sorry? Well,
The delta U be 0?
delta U is 0. If temperature of an object stays the same, it didn't gain any internal energy. So if temperature remains constant, delta U is going to be 0. Now, that means that 0 equals 1,000 minus W. W would then equal positive 1,000 because the piston is going to do 1,000 joules worth of work. And again, from the piston's perspective, it's doing positive work out of itself, so this energy is going to exit it. It's going to, energy is being given to the machine so it can then do this work. So this
That's why I'm
Q is the fuel.
confused. Is it really doing the work if it had to be given energy to do the work?
Well, every machine needs to be given power to function. If the piston just sat here and we did nothing to it, would it ever accomplish its function? So adding the thermal energy to it is giving it the fuel to then perform its task. And this piston runs on thermal energy because when you add thermal energy to a gas, what does it do? A little louder. It expands. So depending on the exact configuration of the machine and various things it's doing, in an ideal situation, when you add thermal energy to this gas, it's just going to get bigger and push out on this end of the piston. And it will expand to the point where it should do the same amount of work that you put into it. Yes?
This might be a dumb assumption. Well, like, when I first read the question, I already was thinking like, why would W not just be 1,000 joules? Because one, work is in joules, so it's already in joules. But if the temperature is the same, can we not, like if it's a problem like that and it says that the temperature remains the same, and this much is being done, can we not just assume that that would be the answer?
You can, it's a reasonable assumption. I'm just showing how the math gets us there too. You are right, but I'm contractually obligated to make sure that you know how this part works. So in an ideal setting, you could put thermal energy into a gas and its temperature would stay constant as its volume increases. That would be the ideal situation. This right here is an ideal machine. You put energy in, it does work from that energy. Looking at the other two quickly, let's say instead piston has 2,000 joules of energy added to it, but it only does 1,500 joules of work. We are adding thermal energy into the system, and it does this much work.
And then would that just be 500?
Yes, delta U, 500 joules. Which means that we gave the piston energy, gas has that energy, it's going to expand and do work, but it doesn't do work equal to the energy it was given. Some of it is left behind. Some of it was just absorbed by the gas, and now it's warmer.
So does delta U correlate with temperature?
Yes. For any object, if delta U is 0, if it's not gaining any internal energy, it is remaining constant in both, in every single possible way. If the internal energy level rises, so if delta U is a positive number, that object's temperature is going to go up. It has gained energy, and that energy is remaining inside of it.
Is it the same for negative?
Yes, if delta U is negative, that means it has lost some of the energy that was inside of it, and its temperature drops. Very quickly, you guys see this part of the board down here? Okay. Very quickly, number 3, delta U equals, we're going to add 500 joules of thermal energy. Meanwhile, someone is going to push in on the piston at the same time. This is 300 joules of work being done into the piston.
So for the piston, it's negative?
Correct. From the piston's perspective, someone is exerting a force into it, and the actual piston part is going to retract inside. Those are negative numbers. From the piston's perspective.
I just got that.
Negative work usually means that the force in the direction are in the wrong direction.
So it'd be
They're
negative.
indifferent. They're like, yeah.
So again, all of this is from the piston's perspective. When the piston does positive work, energy leaves it. When work is done on the piston, it is now gaining energy. So whereas before, we would give it a positive number for energy leaving it, and then the negative here takes care of the fact that energy is leaving it. Here, we plug in a negative number for work, and then that negative is countered by this negative, which completes the idea that energy is now being gained by the object. So when work is done from the outside, if someone outside of the piston pushes in on it, force inwards, distance inwards, now it's gaining energy. So, in this case, why? The object's internal energy level would increase by 800. We have added thermal energy to it. And rather than letting it expand and do work, we have pushed in on it at the same time. So it's gaining energy from 2 directions. And we're not giving it an outlet. So that energy is just going to sit inside of it until something else changes.
And because the internal energy is positive, the temperature will up.
One more time.
And because the internal energy is positive, your temperature will go up.
Correct.
What situation would make you have a negative internal?
Typically, in an actual functioning part of a larger machine, that would be if an example I can think of would be if a coolant system is intentionally taking energy out of something without letting it expand or contract, just to cool it back down. Of these three cases, the first one is an ideal, perfect system. Number one is perpetual motion. You put energy into something and it does exactly that amount of work. Does that ever happen in real life? No. Every single time anything ever does anything in real life, some energy gets wasted because of friction. Every machine suffers from this, including and especially the human body. This right here is an ideal world, and if you can ever invent a machine that does that, congratulations, you've saved the planet, and probably broken physics. Real machines act more like these, where you'll give something fuel energy, it'll do some work, but some of that energy is now trapped in the object, just pointlessly making it hotter. This is why machines overheat. It's why big machines need coolant systems to dump that heat elsewhere.
Why would you do the last one? Why would you put energy and do work on it?
This is, you're right, it's a weird scenario. You add thermal energy into it and you also compress it just to make it warmer for some reason. I imagine this would be a machine where its purpose is just to get hot. I do have something that kind of mirrors that though. It's a demo that's in this particular room. Let's see if I can actually find it. Hey, there it is on the shelf. Behold, the machine you've been talking about. This is a piston. This is not one that can really expand on its own very much though, because I don't have a very good way of putting thermal energy into it. Not very quickly. But this cylinder has air in it, and I'm actually going to add something into it that isn't air. Really, the one day my jeans don't have any lint in them.
Is this where you put a piece of lint thing and it,
Spoilers.
I think it was like that.
There we go. I am adding a tiny amount of denim lint into this cylinder, and then I'm going to reseal it. I hope. I've never had this much trouble with this thing. Okay, this piston is now sealed. No air goes in or out. So the gas inside of it, when I press down on this cylinder, I'm doing work into the system and I'm giving it energy. And currently that gas is surrounded by pretty thick plastic, which is an insulator, meaning we're not really letting that thermal energy escape. Meaning the temperature of the gas is just going to go up. And it's going to look for anything it can do as an outlet. The reason I put some pocket lint in there is because that pocket lint is something that that energy can go into that will visibly combust if I do this right. There it is. Please tell me you saw it. When this works right, and some people saw it, thankfully, because
Yeah,
sometimes when
we're right
it doesn't
here.
work.
I mean,
When I hit the piston, I'm adding energy into the system. That energy goes into the gas. The gas can't do anything with it. It's just going to become warmer and compressed. So it dumps a lot of that energy into the lint and it ignites in that moment.
Can you start a fire like that?
Yes, but even if there was a fire in here for any length of time, it would burn up all the time.
No, like you start it and then you take it off and then you put it on.
Oh.
Well, it would still give out, wouldn't it, because you're like air into the system.
Yeah. Right?
Theoretically, I wouldn't recommend this particular machine for it, just on the grounds that if you put too much lint in there, it won't combust. It has to be a teeny tiny amount. That said, if I do this long enough, it does start to smoke up in there. It's very faint though.
Yeah.
You might have to come do it yourself so you can actually be close enough to see it. Next time, we'll continue examining work done by a gas. And again, the reason this happens is because of expansion and pressure, all related to whether or not its temperature is allowed to change. So more of this to come tomorrow. Have a wonderful day. Stay dry, stay healthy, stay warm, and all that good stuff.